Today we're going to start talking about our last topic before the end of the semester. And to explore that topic, we're going to look at a golf club hitting a stationary golf ball off a tee. Well, the club applies a force to the ball, and the force of the club on the ball equals the mass of the ball times the acceleration of the ball, Newton's second law of motion. Well, mass times acceleration can also be written as mass times change in velocity with time, because that was the first definition of acceleration that we talked about at the beginning of the semester. So I'm going to multiply through by time, and I get the force of the club on the ball multiplied by the length of time the force acts equals mass times change in velocity. Well, we call the force that acts on an object multiplied by the length of time that the force acts impulse. And we call mass times velocity a quantity called momentum. So impulse equals change in momentum. And unlike energy and work, which were both scalar quantities, and therefore the positive and negative signs meant something about whether you were adding energy or subtracting energy, but not direction, impulse and momentum are both vector quantities. So positive and negative signs again tell you something about direction. Well, let's look at another example. Let's say that there's a baseball player who is going to catch a ball coming at him, and the velocity of the ball is 30 meters per second. And when he catches it, he's going to bring that ball to rest. So the final velocity of the ball is 0. Well, if the ball weighs half a kilogram, then the initial momentum of the ball is negative 15 meters per second because of the fact that it's pointed in the negative direction. And the final momentum of the ball is just 0. Now, the units that we get here for the momentum are kilogram meters per second. And you can leave it as kilogram meters per second. Here's one of those examples where we do not make up a new name for this unit. It's also the Newton times the second. So either of those will work. So the Newton second is also a unit. Well, the change in momentum is equal to the final value minus the initial value. And need to get rid of that negative sign there. So the change in momentum is positive 15 kilogram meters per second. This is force times time. And there are two ways that we can do this. We can change the momentum of this ball by applying a very large force over a very short time period. So imagine that you're catching this ball and you hold your arms out straight with your elbows locked. Okay? So you're applying a very large force for a very short period of time. Or we could apply a very small force for a much larger period of time. Imagine that you take your hands, and as soon as you feel the ball in your glove, you move your hands back toward your body. That means you're taking a longer time to bring the object to rest, and thus you need less force to bring it to rest. So this is actually important. Here in this example, If we have a large force multiplied by a small time, let's say 0.02 seconds, then that means the force is 750 newtons. And whatever force the catcher, let's say you, applies to the ball, that's the same force that the ball applies to you, to your hand. Newton's third law of motion. So a 750 Newton force. Ouch. But if, on the other hand, we increase the length of time it takes for the ball to come to rest, say 1 second, then the force can be 15 newtons. That's much more doable. I would rather the ball hit me with a 15 Newton force than a 750 Newton force. Now, the important thing to understand here is that the change in momentum has a fixed value. It's 15 kilogram meters per second because it's going from having a speed to 0. It's being brought to rest. Let's look at another example of how we can use this property to our advantage. Let's say that you step off the seat of a chair. You're standing on a chair. I don't know why. Maybe you're changing a light bulb. But you step off the chair, and now you're going to fall to the ground. Well, just before your feet make contact with the ground, you are going 3 meters per second. You can figure that out from the kinematic equations that we used at the beginning of the semester. And then the floor is going to bring you to rest. So there is a change in momentum here. And let's say that the mass of the person is 50 kilograms. So we go from 150 kilogram meters per second down to 0. Change in momentum, negative 150 kilogram meters per second. So this is a fixed change in momentum because your final speed is going to be 0 and your speed just before you hit the ground is 3 meters per second. So we can do that with a large force over a very short period of time. This would be what would happen if you step off the chair and you lock your knees so that you hit the floor with nice straight legs. Well, if it takes 1/10 of a second to come to rest, that means that there is a 1,500 Newton force that the floor is applying to you. That is 3 times the weight of this person. But if, on the other hand, we actually bend our knees when we hit the floor, then you're increasing the amount of time it takes for your body to come to rest. Let's say maybe 2 seconds. It's probably a little long, but it illustrates the point well, that if it takes you 2 seconds to come to rest because you bend your knees as soon as you hit the floor, then there's only a 75 Newton force that the floor applies to you. And that's much more doable. Or more survivable. Not that you're going to die from this, but boy, it's going to hurt and you might break something. So with the straight knees and nice straight legs, or the bent knees. Well, let's look at an example here. Let's consider that we have a car that, excuse me. Let's try this again. So we have a car that is moving at 23 meters per second. That's about 50 miles per hour. And that the person inside the car has a mass of 75 kilograms. Now, if this car should accidentally run into, let's say, a guardrail, it would be brought to rest, 0 meters per second. And the occupant inside the car is also going to come to rest. Now let's say that the occupant is wearing their seatbelt and the seatbelt brings them to rest in a time of 0.07 seconds. Basically, that's the same time it might take the car to come to rest. Now, there are some ways we can increase that, and we'll talk about that in a minute. So the force of the seatbelt on the person multiplied by the length of time it takes to come to rest equals the change in momentum of the person. So we can find the force of the seatbelt on the person, and that is negative 24,643 newtons. In older automobiles, those that, say from the 40s or 50s, that had those nice steel bumpers and the big steel frames, you could run them into anything and you wouldn't even dent them. Well, that's the kind of car that would come to rest in 0.07 seconds, and so would you, assuming there was a seatbelt in that old car. And that's enough to kill a person. But now let's look at what happens if we have an airbag in our car. Airbags are designed to inflate very quickly and then allow the occupant to fall onto the airbag as it deflates. And what this does is it increases the amount of time it takes the person to come to rest. The car may come to rest sooner, but the person can keep moving as the airbag deflates. So we have the same change in momentum, but with the longer time, we have a much smaller force. Something that still might cause some injury, but not necessarily death. There are other safety features that have been designed into cars over the years. One of which is the fact, if you've ever had a car accident, even just tapping somebody else's bumper, you know that those bumpers can be damaged quite badly. If you run into somebody doing any significant speed, you can cause the whole front end or back end of a car to get crumpled up. Well, that is actually a design feature to keep you safe. Costs more money to fix your car, but at least you're alive to have your car fixed. Crumple zones in cars, that crumpling up or bending up of the front of the car, is done intentionally so that the amount of time it takes the car, and thus the occupant inside, to come to rest is much longer and decreases the amount of force that's then necessary to bring the person to rest. Let's look here at a change in momentum where an object does not come to rest. Here I have a ball, let's say it may be a tennis ball, 0.3 kilograms of mass, moving at 7 meters per second towards a wall. And it hits the wall, bounces back with the exact same speed it had before, 7 meters per second, but now in the negative direction. So momentum initial is plus 2.1 kilogram meters per second. Momentum final, negative 2.1. So the impulse, which is the change in momentum, is negative 4.2 kilogram meters per second. So changes in momentum do not have to result in an object coming to rest. In fact, here what happens is the force of the wall on the ball, first it brings the ball to rest, and then it basically throws it back in the opposite direction. So there is the force of the wall on the ball. It points in the negative direction. First, it slows down the incoming ball and brings it to rest, so it has to point opposite V initial. And then it speeds the ball up and throws it back in the negative direction, so it has to be pointing in the negative direction. So there is the force direction that is acting on this ball. Let's go back to our initial example where we had the golf club swinging down and hitting the golf ball that was initially at rest. And there was the force of the club on the ball. We had that from our very first example. But if the club applies a force to the ball, Newton's third law says, the ball applies a force back to the club. Exactly the same size, but in an opposite direction. So, Newton's third law. Now, I'm going to multiply by the length of time that each of those forces acts. And the time that the club pushes on the ball is exactly the same amount of time that the ball pushes on the club. They make contact at the same instant and they break contact at the same instant. So that time is the same. So I've multiplied both sides by the same number. I haven't changed anything. So we have the change in momentum of the club equals negative the change in momentum of the ball. Or in other words, the change in momentum of the club plus the change in momentum of the ball equals 0. So in other words, if one of these objects loses momentum, the other object has to gain that exact same amount of momentum, because the total momentum has to stay the same. This is the conservation of momentum principle, and it's the last equation on that list that I wrote at the very beginning of the semester. If you go back to your first page in your notebook, after work energy came conservation of momentum. Now, while mechanical energy is not always conserved, momentum is, and this is really convenient. So conservation of momentum says that if, let's say, the golf club loses momentum, the golf ball has to gain that same amount of momentum. The total momentum of a system of objects that are applying forces to one another is always the same number. Well, change in momentum of the club is its final value minus its initial value. And negative the change in momentum of the ball is its final value minus its initial value. I'm going to distribute that negative sign in there for the ball. And now what I want to do is I want to get all the initial values on one side of the equal sign and all the final values on the other side. So the conservation of momentum equation that we got as a result of Newton's third law, it is a consequence of Newton's third law, can also be written this way. The sum of all the initial momentums in a system of objects applying forces to one another is equal to the sum of all the final momentums. This is another statement of momentum conservation. So, momentum conservation says sum of all the momentums before equals the sum of all the momentums afterwards. Well, before and after what? Well, some event, something happening. Like in this case, the club hit the ball. So it's a collision. But it doesn't have to always be a collision. It can be a throw, a catch, a collision, a drop, a bounce. But when you're reading a problem, what you're actually looking for are action words, verbs: throw, catch, collide, hit. So let's look at this golf club example. Let's say that before the hit, the collision, We have a 0.07 kilogram ball with an initial velocity of 0, so it has no momentum. And we have a club of 0.8 kilograms moving at 20 meters per second as it comes in horizontally to hit that golf ball. So the total momentum before the collision has to equal the total momentum after the collision. And the total momentum before is 16 kilogram meters per second. So that's got to be the total afterwards. So event happens, hit. Afterwards, the ball, let's say, is moving off with a speed of 100 meters per second. Let's find what speed the club is moving with after the hit. So the momentum of the ball afterwards is 7 kilogram meters per second. Since it plus the momentum of the club still has to equal 16 kilogram meters per second, that means there's only 9 kilogram meters per second of momentum left for the club. And you solve for its speed, and that's 11.25 meters per second. So the ball gained 7 kilogram meters per second of momentum, and the club lost that amount of momentum. It basically just transferred from one object to the other. All right, let's look at another example, conservation of momentum here. Let's say that I have a train car with a mass of 2,000 kilograms, and it's moving at 5 meters per second along a train track, and it's going to collide with a hand cart. You've probably seen these in movies. People stand up on them and they push the little handles up and down to make it go. Well, our hand cart is initially at rest. So our hand cart has a mass of 800 kilograms at rest, and the train car, 2,000 kilograms, moving at 5 meters per second. So what's the event? Well, again, it's going to be a collision, a hit. Okay. But after the collision, instead of moving off separately the way the golf ball and the golf club did, these things are actually going to stick together. If you've ever seen train cars collide, you know that they have these devices that connect them to one another. So the train car and the hand cart are going to be stuck together after the collision. This means that after the collision, they're going to have to move with the same velocity. If they are physically connected to one another, they have to be moving with the same speed. So let's apply conservation of momentum. Sum of all the momentums before equals the sum of all the momentums afterwards. So we get 10,000 kilogram meters per second is the total momentum before, and that's going to be the total momentum afterwards. Well, we have two things that are moving afterwards. We have the train car times the combined speed, and we have the hand cart times the combined speed. Since the speeds are the same, we can undistribute that. And so when we solve for the final velocity of these two things, we get that they have a speed of 3.57 meters per second. And now that we know the speed, we can find the final momentum of each of these objects using their mass and that combined speed. And when you add them together, you get 10,000 kilogram meters per second. Momentum is conserved.